Okay, welcome everyone. I'm glad that you are here again. Thank you for continuing with this course on Precalculus. So today we will tackle the second solved problem, that is this one. Okay. Remember we are using this book that is the Sham Outlines Precalculus. So if you want to go over the theory or the first examples, you can do this uh, pretty quickly. So because of that, I love these kind of books because the examples are directly delivered to you with the necessary information. But remember, this is more like a workshop, so we will work on this. Okay, so that's it. Today we'll check something related with a subtraction. So we will check some terms about this. Okay. So let me open a new whiteboard. Okay. Let me log in. Okay. Let me have this. It's another tab. Mm-hmm. We open a new whiteboard and let me create this one. Okay. So we have to prove the distributive law, but for subtraction, and it would be a great exercise because we can just go with the properties to understand the properties. So let me just write a proper title. Okay, and well, the idea is this. As before, I will write the statement of the exercise just as you see in the book, but I want also. Okay, let me have some. We have to prove that a multiplying b minus c equals to the subtraction of the multiplication. That's it. That's it. Okay. Well, here what is missing is that we have uh, to state for which kind of numbers. Remember, so we state this one. This is not part of the initial statement, but it's important to know which kind of numbers we are trying to use. Also, remember this notation means the first this means sorry, belongs to, and this notation is just real numbers. Okay. For me, it's important that you know this kind of notation because in most of the quizzes, the tests that you will take for the university, probably it's very likely that you will see this kind of symbol. So it's necessary to that you know this about these symbols. Okay. Then let me move a little bit more. Here we have to have in mind what does it mean to have a subtraction, okay? From an algebraic point of view, not the algorithm to subtract two numbers, but what it does mean in the context of algebra to have a subtraction. and it has something to do with some actions. The first one action I don't want to enumerate this, but so let me just use action in this case. Is that for every, well, indeed, let me use the notation again. This quite a strong notation. This symbol that looks a little bit weird is it means for all. Okay, so it's a good idea to to learn what each symbol means. We can just write for all, but well, in this case it means for all. Let me use real numbers again. So for all real numbers, for every, you can also say, well, not for all, but I think it's better to read this like for every. And as you can see, now we have this notation for every real number, and then we state that exists, okay, another quite strange symbol. Remember, this should be read as exists. Of course, another real number because we are working with real numbers. Okay, okay, such that. Indeed, this is like a change, so this dots right here means such that. And the statement is this one, okay? A plus B equals to 0. Okay, and this is it. A plus B equals to 0. And well, there is another action. Here in algebra we use a lot of actions because algebra is like the abstraction just of arithmetics. So what we learn in arithmetics is just the basics of algebra, but we try to abstract this. And the idea here is that, well, let me check what is going on with my connection. There is another action. So from the algebraic point of view, we have to be aware of this. There exists an element called the 0. So exists some element called 0, such that for every real number, check here, we are switching the position of these two symbols. This 0 is for every real number. And the property that defines 0 is that a plus 0 is equal to 0 plus a, and this is a neutral element. Okay, this is called the 0. Is called also the neutral element for addition, okay, or subtraction. Okay. This is important because that's the meaning of 0 from an algebraic point of view. Indeed, it could be proven that in the case of real number, the 0 is unique. And well, in most of these numeric systems that we know, this is important because these kind of actions that, remember, an action is like a basic rule for a numerical system. These actions are shared in many other numerical systems. Let's say, for example, if you work only with integers, if you work only with rational numbers, real numbers, for example, or even more with complex numbers. In each of these systems, there are a number called 0. Okay, we can identify following some inclusions that, or in the terms of the mathematical jargon, is an embeddings. We can embed the 0, for example, from the integers into the 0 of the rational numbers, and so on. So each system has a 0. So of these kind of systems, and the 0 is neutral. The neutral element of these systems. Okay, And the idea of the axiom above is that for every number, a real number, remember we are working just with real numbers, you can find another number, another real number that, let's say when you add those numbers, you get 0, okay, the neutral element, okay. In that case, let me use another color, maybe a green one. That number is called inverse. And indeed, it's unique. We won't prove that right here. But since it's unique, you can just call this number like negative a. Okay? So please be aware of this. Be aware of this. This negative sign that you see is just notation. Okay? It's just notation. And this is pretty important because when you see a negative sign, don't get into the trap that this is a negative number. Okay, we will see the rule of the signs, and so we will see that something like with a negative sign not necessarily is a negative number. Think in this number. You can put this negative sign at the front of the negative one, but this is just one, and this is a positive number. So be careful if you see a negative sign in front of another number. That doesn't mean that the number is a negative, okay? Because of this rule of the sign, you can see that that not true for every number with a negative sign, okay? Well, in other words, you can restate this. You can restate this action like saying that if you have an a plus negative a in whatever order you want, it could be 0, okay, just like that. There is no there is a way to say this, but be aware when you get this, well, it's not common to write this in like in a exercise. So by definition, when you say, okay, we want to define a subtraction. What is a subtraction? By definition, let me use this symbol with an equal like with adult. This is just notation to say, well, you know what? We want to add a with the inverse of b. Okay, whatever it means. Okay, that is just a definition. Well, that's quite abstract. So let me do this in another way. So just let me see if I can't. Oh man, no, I don't want to do this. Okay, I have to use the mouse. I don't like it, but okay. Let's see how it works. For example, from an algebraic point of view. Okay, what it means to have 5 minus 3. Okay, let's do this. We know for sure that 5 is 2 plus 3, right? Okay, well, also we know from the definition that this is like adding the negative or the inverse of 3, okay, just by definition. But yesterday we learned something about the associative properties, so we can just add this one. Sorry, not this one. We can change the order of the parentheses, and by definition, it is just 0, but the 0 is the neutral element of the addition, so 2 plus 0 is 2. Well, this is a long way to, to do a subtraction, but I want you to know what is that true, okay? Why 5 minus 3 equals to 2? Well, we know that, okay, but it's okay. So please be aware of this. Please be aware of this. And well, it will be important because sometimes we have to change the way that we think about this. Maybe when you get 3 minus 5, the resulting expression will be different, okay? So because of that, we know we have to have in mind this kind of definitions right here, okay? So that's it. Well, everything that you see here will be applied to the current exercise, and the exercise is not that difficult. I guess that is not that difficult. Let me go above and take this. So if in some exam you have to follow, for example, order the steps of a demonstration, you can remember this. So you have this one. Okay, so we can restate the subtraction like an addition. In this case is b plus the negative of c. Okay, and you can multiply a times b plus a times c minus c. Okay, and now at this step we have to have something else that is called the rule of signs. Okay, so I want to explain you this because this kind of rules could be somewhat um, quite strange to use the first time, because this thing that the negative times negative is positive, positive times negative is negative, and anything else could be quite difficult to grasp the first time that you see this. But let's check this expression. Okay, let me stop at this point and use this expression. This is another thing. Okay, so we have seen that if we have well, let me stop. Let me make a claim right here that is unique. Okay, what it means that even if you rewrite the element in many forms, you can do this. The inverse will be every time the same. So assume that we have two numbers with the same property. Let's say that we know this, and well, let's assume for a moment that there is another number b prime. Not confused with that derivative. That's not the case. Okay, in this case we have this number. Okay, so let me check this one. So we can subtract. So let me take this one. Let's say that we add both sides b prime. So we have something like this. Because of the association, we can just omit the parentheses from one moment. And well, we can use another action that is the commutative property. So we can just change these two. Okay, but this one makes 0. So in that case, as you can see, let me open here. Sorry, my tablet is doing something weird with this kind of lines, but okay, you can eliminate that one because it is just 0. And so both inverse are the same indeed. Why this is important in our exercise, why it matters in this case. Okay, well, remember this is just an abstraction of arithmetics, so be careful. The idea is here that if we have some actions, we can deduce many properties for many other numerical systems. In this case, those systems that we are trying to work with are called rings of numbers. You can add some properties like commutation, the neutral element for multiplication. Some rings has a inverse for multiplication. So you can add some other ingredients, but the properties that we are seeing here are common for any ring, like the integers, like the fractions, like the real numbers, like the complex number, like the matrices, for example. Yeah, matrices is a ring. No, I don't. I'm not sure. Well, not because. Okay, let me think of that. I don't remember. It's an algebra, but I think that is a rig for the addition. Okay. So why is that? What is important? Okay, because for another claim, but let me let me write this in another color. Let's think about this number. Okay. No, indeed. Let me use C. Something like this. Okay. So C, in this case, we are adding A times the negative C, the inverse of C. Because of the addition, because of the distribution law applied in the other sense, we can just factor A. Remember, the distribution is what we see yesterday. And because of the because of the implication of C plus negative C, this is 0. Let me just do this. A times 0, you maybe will say this is 0 because we learned that from the elementary school. Okay, let's use that, but we have to prove this again. Okay, so we got 0. Well, what it means is that this number that you see here, let me use another color, this number is the inverse of A times C. So because of that, we know that this quite strange number is just the negative of A times C, because the negative is unique, okay, because of the claim above. Okay, give me a second to prove that A times 0 is again 0. But in this case, we can claim that this one is just a because of the claim, the previous claim. Remember that is just a plus b, ab plus the negative of ac. Okay, but well, by definition of subtraction, we have this one, and well, in this case, we can just omit the parentheses, and we have our claim. Okay, be aware of this. You can say, oh, there's a lot of things just to prove an identity, a trivial identity. We have used this maybe for many years. If you are in the high school, you have seen this a lot of times. But this is important because in this way we can abstract the rules of arithmetic and have just a very basic set of rules that are called axioms, and from these axioms we can deduce a lot of another properties. Okay, you can do this with other kind of systems, but that's the important part. You can deduce this kind of axioms. By the way, just to be clear, you can consult some of these actions right here. Okay, as you can see in the book, you can have a list of actions. I don't want to explain you this again because I don't want you to take a lot of notes, and because those are in the book. Okay, so you can just see the book, see some example about those actions, but I want you to see these actions in action. Okay, so because of that, I am omitting to enumerate every action and just using this in the in these exercises. Okay, well, that comes to the other property, not property, but it's another statement that is called a proposition. Let me call this a proposition. And it's very interesting because most of the time we just give this proposition for granted and say, well, A times 0 is just 0 again. Okay? Here it's just 0. Okay. But why is that? Why is that from an algebraic point of view? Okay? So let me take this expression. And well, from the axiom of the neutral element for addition, we know that we have a0 plus 0, 0 plus 0 is 0, okay? Trivial, right? And because of the distribution law, we know this. Okay? Okay? Yeah? Trivial, okay? Okay? Just the rules. Let me Let me rewrite everything. But also, I don't know which number is that. Well, we know, but let's say we don't know which number is that, but we know that there exists a lot of symbols, sorry because of that. But I want you to know the way that we think in mathematics, how to prove these things using just pretty elementary properties. So let me take this. Let me take this down. This expression. Oh my god! I think it will be better to meet this. So we know that for sure there is a inverse for a times 0. Okay, it's an element for a times 0. Indeed, I forgot one parenthesis. Let me use this notation. I don't want to be so strict with the notation. I want to give you the ideas. So in the other side we can just subtract this. In the other side, I don't know which number is this. Of course it's 0. We can prove that. But well, in that case, this number will cancel and give us 0 again. Okay, we can cancel this number, and using another property. It's not the case here to to mess with parentheses, but we have at first parenthesis here. We can translate the parenthesis here, and we can cancel just this, and it will be 0. So in the left hand side we have 0, and in the other we have a0 plus 0. But remember, 0 is the neutral style, the neutral element. It's just the neutral element. And so we have this expression. Okay? Because we can just add 0 to the right hand side, and this is it. We have again a times 0. Because of that, if you take any real number and you multiply that by 0, you will obtain 0. But remember, this is not a fundamental rule of this kind of numerical systems. You will hear about many explanations, and if you have a quantity and you multiply by nothing, so because it's nothing, it's empty, and you will get empty again. Well, that is like a philosophical explanation from this for this rule, but that's not the algebra. Okay, the algebraic way to think about this is apply the basic rules. So we know this this part for sure. It's because 0 is plus 0 is 0 because of the action of the neutral element. This one is just the distribution law. We apply here a lot of rules, but basically we subtract a times 0 from both sides. In one side it gives out 0. In the other side is a0 times a times 0 plus 0. But we know that the addition with 0 is neutral, so we get just a0, and in that way we know now, we are sure that a times 0 equals to 0 because of the fundamental rules of algebra. Okay? Okay, be aware of this. This is pretty important because we are doing algebra. Okay? And so as you can see, this rule, it's not necessary to do every calculation every time when you need this identity, for example. But it's important to know the fundamental rules, because sometimes you will need to apply this kind of rules in other contexts. Okay, and it will be better to do this to know this rule, to know what you can apply and which rules, which operation are not valid in another context. Okay, so that's it. Well, for today is enough, I think. So we explained the exercise number 2 from the solved problem of the first chapter of this book. And well, if you join tomorrow, I will explain the third exercise. Okay, this step that you see here will be explained in more detail. Okay. Well, for now it's enough. So I appreciate that you take your time to join me in this lesson, and well, see you tomorrow to continue with our assignments. Bye.